Hi, everyone. My name is Amir, and today I will present my final project of the course Machine Learning Foundations for Product Managers under the course AI Product Management Specialization held by Duke University and Coursera. This project is focusing on building a machine learning model to predict net hourly electrical output, or PE, in megawatts for a combined cycle power plant. And also, I will analyze between random forest, linear regression, and gradient boosting. Okay, so for this task, we use 9,568 hourly sensor readings with 4 inputs. The first one is ambient temperature, or AT. The second is exhaust vacuum, or V. Third is ambient pressure, or AP. And the last one is relative humidity, RH. Now, the goal is a reliable regression model that turns these ambient conditions into an accurate PE forecast. Okay, so I compare several approaches in this task. I started with a dummy baseline, and also compared with linear regression, random forest, and gradient boosting, and eventually selected the model that generalizes the best outcomes for us. Now, the rest of the talk walks through the evaluation plan, the results, and what drives their predictions, which I will elaborate later on. Okay, so this is a regression task. So we need to predict continuous power output in megawatts. And I used RMSE as the primary metrics because it penalizes large mistakes. It's reported in megawatts, so it's pretty easy to interpret. And I also show MAE as an average miss in megawatts, and R squared to indicate how much variance the model explains. Together, they give both accuracy in real units and overall fit. Okay, so as I said, this data set has 9,568 rows and no missing values. Relationships are not strictly linear in this case, especially for temperature and vacuum. So I aimed for a fair generalization estimate and not just fitting the training data. Okay, so I held about 20% of the data as a final test set. And on the remaining data, on the remaining training data, I used fivefold cross-validation to compare models. So we need to put about 20% of the total data aside as a final test set. This will reduce variance and will prevent any test leakage. Okay, so I started with a dummy regressor that always predicts the mean PE. And that's actually sets the floor or the baseline for any real model that needs to beat it, as I will show in this presentation. Okay, so I compared here between 2 families. The first one is linear regression, which is fast and interpretable. And the second family is tree ensembles, random forest, and gradient boosting that can capture nonlinearities and interactions without manual feature engineering. Okay, so I'm using fivefold CV, and I found that random forest gained the lowest average RMSE, so I selected it. Small grid search refined it to 400 trees with unrestricted depth and a minimum samples of leaf 1. Okay, so the final model is a random forest with 400 trees. And on the held out test set, it achieves a test of RMC of 3.23 megawatts and MAE of 2.32 megawatts. and R² of 0.964. Now, these figures are from the untouched test set, so they reflect an expected generalization. Okay, the scatter graph here compares predicted versus actual tests values. The tight clustering that we can see here around the diagonal shows a good calibration and a small residuals across the range. So it means that we did quite good with our choosing our ideal model here. And for the interpretation, I looked at feature importance. Ambient temperature, AT, and exhaust vacuum are the dominant drivers here, with pressure, AP, and humidity, RH, contributing smaller but still meaningful effect. Okay, so why did I choose this approach? I used this workflow to prove improvement over baseline, rely on cross-validation for robust selection, also to balance interpretability versus non-linear accuracy, and keep a signal final test for unbiased estimate. Now, what would I do for the next steps? So with more time given here, I would explain turning the random forest to maybe try XG boost or gradient boosting with a bounded grid. And also, I will add a partial dependence or a SHAP for deeper explanations, as interpretability can be valuable here for our end users and customers. So thank you for listening, and bye.